Yeah, okay. There we go. Okay. All right. Well, thanks, everybody. Finally, again, thank you, Peter, for remembering that. So welcome to Battle Point Astronomical Association. Some of you are members. I recognize you here. If you're not a member, you can join. And I do want to say that our membership dues are going up January 1st. So if you want to join now before that, you can take advantage of the old rates. It's $30 for a family membership. What is it? $20 for an individual membership and $10 for a student under 18. And those are going up to $40 for a family, $25 for an individual, and the student membership will stay the same at $10, effective January 1st. So there you go. This is the John Rudolph Planetarium, this room with the dome in it. And we used to have a projector that would project on this dome, and about 5 years ago, the projector died. So right now we're fundraising to purchase a new projector. So if you'd like to make a donation to support the planetarium, we can take credit cards, checks, or cash, whatever, that you can help us get our new projector. And we hope by the end of the year to be able to offer planetarium shows in here. When the weather is crappy and we can't have star parties, we can still do things in here. Okay, so and then after tonight's program, we're going to have a star party up on the roof. Nels is out in the parking lot with his telescope, so you can go see what he's up to. Upstairs, we'll have a 9¼ inch celestron set up looking at the Moon, Jupiter, and Saturn. The Ritchie telescope has been fitted out with cameras, so we won't be able to use it for visual observing. But Cole is up there, and he'll tell you all about what we're doing up there.
A question: is this going to be a permanent scenario?
What?
That we're using cameras?
Yes. Yeah. We're converting the Ritchie over to be for astrophotography, and we won't on a regular basis. We won't be doing a visual with it. Okay. Let's see. So that's everything I wanted to talk about. So our speaker tonight is Dennis Conti. He's a retired telecom professional, and he's an amateur astronomer with a strong interest in exoplanets. And if you remember our speaker if you were here for our speaker last month, we had Natalie Allen talking about exoplanets, and she did a really nice job telling us all about that. And Dennis is going to continue the conversation and talk to us about how amateur astronomers can participate in exoplanet research. In 2015, he founded the AAVSO or AAVSO or AAVSO. I'm not sure how they like to say their acronym. You can correct us on that, Dennis. Anyway, he established their Exoplanet Section and continues to lead that section. And so he'll be telling us all about what they do. Okay, that's it. Stand by, and we'll get Dennis back on the screen. And let's see, change to the other camera so you can all see yourselves. And Dennis, let's see. How do I pin to second screen?
Can I see the back of your head? No.
Oh, there we go. Okay, Dennis, take it away.
Okay, thank you, Frank. Let me go ahead and share my screen here. Whoop, sorry. Everybody see that okay?
Yeah, that's great.
Okay, great. Well, thank you all for the invite for tonight. I hope that my presentation will be both entertaining and enlightening. I guess you did have a talk last month on exoplanets, so hopefully there won't be much overlap here. The title, as you see, Wacky World of Exoplanets, How We Discover Them. What I'm going to be talking about are the different types of exoplanets that we have come to know and love, and also how we being amateur astronomers, have helped with the discovery of those exoplanets. What you see in this picture here, this is actually an artist rendering of exoplanet LTT 1445AB. We give sort of strange names to exoplanets these days. And what's strange about this exoplanet is it has 3 suns, one of which you see in the upper left that it orbits, and 2 other suns which are orbiting each other that also are visible from this planet. So this planet literally is in daylight almost all the time. So it's one of these exoplanets in this strange, wacky world of exoplanets. What I thought I would do to start off is just tell a little story about how I got involved in exoplanet observing. As Frank indicated, I myself have been an amateur astronomer for a while. I started off with visual observing, then got into imaging using standard CCD camera. I was doing some planetary imaging back in 2015 and looking at Jupiter. Jupiter at that time then got to a point where it was below the horizon, so there wasn't much to see. I was on this forum of other Jupiter observer interested people, and someone came on the forum and said, why don't you all start looking at exoplanets? And I thought to myself, well, that's kind of strange. How can we on Earth with our little backyard telescopes observe a planet going around a distant star? But lo and behold, as I got into that field, indeed, I did find it not only possible for us amateur astronomers with our backyard telescopes to detect the transit of a planet around a distant star, but also to help with our professional astronomer colleagues in the confirmation and discovery of other exoplanets. And I hope to show you a little bit later how you who are involved in imaging with your own telescopes can in fact get involved and participate in exoplanet science. What I'd like to start with is the big picture. We sometimes get wrapped up with some of the interesting things that we're doing from a technical point of view, but I think it's important to kind of step back and see where NASA and the rest of the exoplanet science community really sees as the big picture. And it's very simply to see if there are planets outside of our solar system, which of course we call exoplanets, whether or not there's any signs of them supporting life. We believe that in order to support life, the planet has to have some hard surface, namely it has to be rocky. That means we have to come to some understanding as to the density of the planet. We of course believe that it should support some kind of liquid water on that surface, since at least as far as we know, water is essential to life, at least as far as we know it. We'd like to see if there's an atmosphere on that exoplanet, that atmosphere being also indicative of some type of signatures we call biosignatures, which again are indicative that there has been or is life on that planet. And we'd like to understand which of those biosignatures we can rely on that give us confidence that life exists on the planet. We now are finding that when we see elements like oxygen and methane in an atmosphere of an exoplanet, which we are starting to be able to detect more and more of, we now are realizing that some of those elements can be derived not necessarily from biological mechanisms, but in some cases by geological mechanisms. So the whole area of exoplanet atmospheric science is now grappling with what biosignatures can we really have confidence in will tell us that there's life on those exoplanets. I'm willing to bet, not having seen it, that your presenter a month ago probably was talking about using the James Webb Space Telescope to take a look at using spectroscopy in the infrared what elements are in the atmosphere of exoplanets, which is exactly what we're trying to detect and understand better. And finally, the whole area of exoplanet science then is helping us answer these questions. Interestingly, if you look at these 5 questions, we're actually now down to the 4th, if not the 5th. And James Webb Space Telescope is going to be helping us answer this 4th question of not only what's in the atmosphere, but can we start detecting some biosignatures? Exoplanets are now, we know, circling most stars we see in the night sky. And we now know that there's not only one, but in many cases, more than one planets orbiting those stars. We, of course, can't see them because they're so small and the contrast difference is so great between the star and the exoplanet that we really can't differentiate them by observing them. Some exoplanets pass directly in front of the star from our point of view. We call those transiting exoplanets. Many, of course, don't. Many, of course, are orbiting the star in a circle around the star, and those are a little bit more difficult to detect, but there are mechanisms for doing that. As we'll see, exoplanets come in all sizes, from Earth-sized planets to very large giant planets, such as the size of Jupiter or even greater. Now, looking at the different kinds of exoplanets, one of the most common exoplanets that were initially discovered are so-called hot Jupiters. And their name derives from the fact that they're very large, namely Jupiter-sized planets, and they're very close to their star and therefore hot. Very much unlike our solar system, of course, where Jupiter is much further out in the solar system. So we have discovered many of these hot Jupiters that are orbiting stars at least the size of, for example, our own sun. We have found many planets orbiting a star. In this case, what you see here is the TRAPPIST-1 system, which we have discovered 7 planets orbiting their host star. And in fact, about 3 of those planets are in what we call the habitable zone. Namely, they're at a point from the star where liquid water theoretically could exist. We have some planets that are orbiting a star, but that star system might be orbiting another star, just as you saw on that introductory slide. So we have examples of multi-star systems with a planet orbiting one star and that system orbiting another. We also have planets that are free floating, that for whatever reason have gotten ejected from their original solar system and are orbiting free in space. We interestingly have some planets that are orbiting in the opposite direction from the spin of their star, which is sort of curious because the way, as we'll see a little bit later, the way a planet is formed is it's part of the original formation of the star in terms of the disk that is circulating that created the star also in many cases creates the planet. So for a planet to be orbiting in the opposite direction, again, is curious. And this might be because that planet was captured by that star. And finally, we have planets that we see are starting to disintegrate around their host star. And we see some evidence of partial parts of a planet that are transiting across their star. So as you see that there's no one characterization of an exoplanet. They come in different numbers around their stars. They come in different categories as far as what stars they're orbiting and even the direction they're orbiting. So before we talk about how exoplanets are formed, I think it would be good to talk about how their host stars are formed. I couldn't help, of course, put up How a Star is Born with this little picture of the movie that came out recently. I just thought, when I thought to myself, "A Star is Born," immediately that popped into my head. But let's take a look at how, in fact, a star is born. One of the famous pictures that just came out with James Webb is this one. This is, in fact, a star forming region. And what you see, that cloud of dust and gas, is in fact where new stars are being formed. Now, how star formation takes place is the following. There's this gas and dust cloud that then results in clumps being formed. Imagine a ice skater that has his or her arms outstretched, and as the ice skater brings their arms closer in, they rotate faster and faster. The same thing is happening with these gas and dust clouds. As gravity pulls in some clumps of dust and gas, that attracts more and more. There's greater and greater circulation that happens. The cores get denser and denser. And what happens then is young stars start forming from these disks. Not only does that happen, but if you can imagine now a pizza dough being thrown in the air, what happens is it sort of starts spreading out because of centrifugal force. So the same thing happens with a star in the middle with its gas and dust around it. There becomes this flat disk that starts forming. And in that flat disk, in fact, is where planets begin to form. And this picture you see here is in fact a image taken with a ground-based telescope that in fact shows the different rings of a disk around a newly formed star. And those gaps in those disks, we believe, in fact, are new planets being formed that are clearing those disks, very much like the disks around Saturn. So the planet's formation begins with its host star being formed. And as I said earlier, if the star is circulating in one direction, the gas cloud and the disk around it is circulating in the same direction. And therefore, we would expect that planets that are formed would orbit in the same direction as the host star is spinning. But as I said earlier, there's some examples where that is not the case. So in any case, this is how stars are formed and how planets orbiting them are formed. So again, to summarize, the material from the young star's disk starts clumping together. The core of the planet starts forming. Some planets will form very close to their host star. Some planets will form at a distance, but then migrate inward toward their. There could be gas giants, such as our Jupiter. There could be ice giants, such as Uranus, and there could be rocky planets, such as Earth. And we see in some cases planetary systems on other stars that have some or a combination of these different types of planets being formed. And in fact, a planet itself can have its own disk of material that then forms into moons around the planets. We're just starting to think that we might be able to start detecting exomoons, and moons going around exoplanets. So stay tuned on that. So how do we discover exoplanets? Well, one of the most popular methods is the transit method. So when a planet passes in front of the host star from our line of sight, then what we'll see is a dip in light of the star as the planet goes in front of it. Now, this dip in light is about 1% That's the range that we amateur astronomers can observe. But some of the space-based telescopes and some of the professional observatories can detect even something down to 0.1%. So the transit method relies on this dip in light of the star as the planet moves in front of it, again, from our line of sight. For those planets that orbit the star in a circular motion, where the planet is not moving in front of the star, there are other methods, and a very popular method is the radial velocity method. In this case, if the planet is orbiting the star, it's going to cause the star to move, in the case of it being sort of in our line of sight, it's going to cause the star to move backward and forward from us. And very much like a train moving away from us or moving toward us, where there's a change in pitch, what we see there is a change in the spectrum of that star, a red shift or a blue shift. That shift, that Doppler effect, will inform us as to the mass of the planet. In the transit method, we're able to get the radius of the planet, not the mass. In the radial velocity method, we're able to get the mass of the planet and not so much the radius. So if we're able to look at a planet with both methods, and we're able to get both the mass and the radius, then we can get the density. And knowing the bulk density of the planet will help inform us as to whether in fact it is rocky or whether it's gaseous. So the combination of these two methods are what help us understand, again, the characteristics of the planet itself. There are other methods that also astronomers use to detect and characterize exoplanets. One is called microlensing, which is relying on the fact that as a body of material passes in front of another body, especially if we're talking about large bodies of materials like stars, the background light of an object will bend around that foreground object. If the foreground object is in fact a planetary system, such as a star and an exoplanet, then from the amount of light that is bent, we're able to determine the characteristic of that exoplanet, in particular the mass of that exoplanet. So there are other methods, but the transit method and the radial velocity method are the most popular. So I'd like to spend a little bit more time on the transit method, since this is the dominant one used by both professionals and amateur astronomers. And as you see in this little cartoon here, as a planet goes in front of its host star, if we're keeping track of the light that we're able to observe from our telescope on Earth, we see that there's this characteristic bucket-shaped curve as the planet goes in front of the star. And again, that dip in that curve is on the order of 0.1 to 1%, maybe 2%. So the curve that we see in this transit method is the result of observations we're taking. And sometimes that the length of that observation could be on the order of 6 hours. So in a observation that I might be taking from my backyard telescope, it would be almost an all-night observation where the observation prior to the dip in light and after the dip in light might be each half an hour or an hour, where the dip in light, the transit in the middle, might be on the order of 3 or 4 hours. There are some that are shorter, some are longer, but generally it's about an overall 6 hours kind of observation from beginning to end. So it does require a dedicated observation session throughout the night, recording the data from the light of a given star, and then tracking after, doing an analysis to see how the light has changed over that observing period. That's basically the method, the transit method that's used. Now, from that light curve, we learn a lot about an exoplanet and its host star. In particular, what's important is the duration of the light curve, the depth of the light curve, and even the shape of the light curve. And from those simple things, we can determine the size of the planet, because the larger the planet is, the greater the depth is going to be, because there's going to be more light that is going to be blocked out. We can get the size of the orbit. How long does it take, and how large an orbit is it to go around its host star? And we can get the inclination from our line of sight. So simply from the light curve, we can characterize a lot about the exoplanet. So how were exoplanets discovered? And what I'm going to use as an example here is the current workhorse that NASA is using for discovering exoplanets. And it's a space telescope called TESS, standing for Transiting Exoplanet Survey Satellite. And as the name implies, it's focusing on star systems that have planets that are transiting their host star. And it's doing a survey, in fact, an all-sky survey. So what TESS has been doing for the last 4 years has been taking images of the entire celestial sphere. So for every 27 days, the TESS satellite has 4 cameras, and it's dwelling on, for example, a sector in the northern celestial sphere for those 27 days, constantly taking images of stars in those fields. Then it will move to the next sector. So over the course of a calendar year, it will cover both the north and south celestial sphere. We are now into the 4th year of TESS. We've already surveyed the celestial sphere twice, and we're going back again to look at sections that have been missed in some of the first 2 observational runs. So TESS is going to be, after all is said and done, we'll have looked at probably close to about 98% of the entire sky, looking for transiting planets. Now, if you look at this picture, and especially look at the very top, you'll see that this is where many of the sectors overlap. So whereas it would be the case that some of the lower sectors are only going to be observed by TESS for 27 days, and therefore would be restricted to discovering exoplanets who have orbital periods, either half of that or maybe even a third of that, TESS is not going to be able to see planets that are orbiting, let's say, 365 days, except for where those sectors intersect at the top, where there's almost continuous coverage. And in fact, that's called a continuous coverage zone. And it's that continuous coverage zone where exoplanets that are orbiting for longer periods of time, and therefore further out from their host star, will be discovered. And it's those planets also that are candidates for follow-up with the James Webb Space Telescope, which I'll be talking about later. So as far as the TESS mission, as I mentioned, it launched 4 years ago, April 2018. It's been conducting all-sky surveys of bright and nearby stars. By nearby, we mean 30 to 300 light years. Those of you who have heard of the Kepler mission, Kepler was doing a survey of a very small part of the sky and was looking at stars further away than TESS has been. So TESS is looking at closer stars and brighter stars than Kepler. Excuse me. As I indicated, TESS is going to be finding Earth and super Earth-sized planets that will be passed on to James Webb. They'll characterize their atmospheres. One of the other images that came out in the initial James Webb introduction, you may have seen a sort of curve of a graph of data points in the infrared and near infrared, showing the existence of water and water vapor in the atmosphere of a particular exoplanet. And your speaker maybe a month ago may have in fact talked about that. So many of these candidates that James Webb is going to be exploring their atmospheres for are coming from TESS. So far, TESS has discovered 5,800 candidates, but has confirmed 231. There's still a lot more to go to try to confirm. Now, we make a distinction between candidates and confirmed because we go through a very rigorous process to make sure that what we think is the signature of an exoplanet, let's say we see one of these dips in light, we still have to go through a very rigorous process to confirm, in fact, that's an exoplanet. Because as we'll see, there's many false positive cases where what we think is an exoplanet really might turn out to be two stars that are orbiting each other as opposed to a planet orbiting a star. So to be absolutely sure that we are looking at an exoplanet, we do go through, as I said, a rigorous process. And this is where amateur astronomers play a huge role in helping with that confirmation process. So let me say a few words about this entire confirmation process. Then I'll show where we amateur astronomers play a role. It starts with us on the ground following up and taking images of candidates that TESS thinks it saw a dip in light of. So we do ground-based follow-up. If it passed through a fairly rigorous set of tests that we impose on those observations we're taking from the ground, then that candidate is passed to some of the professional observatories that are looking at high resolution imaging, namely looking at these candidates through very large telescopes to see if we can see any nearby neighbor that might be affecting the observation and posing as a false positive. If that succeeds, then we also do some spectroscopy to look at the star itself to improve some of the characteristics of the star, because we need to make sure that we understand the star better in order to understand the planet better. And finally, we would do this Doppler thing I mentioned earlier, where we hopefully can determine the mass of the planet. But it all starts up at the top with these ground-based follow-ups. And this is where amateur astronomers and professional astronomers play a huge role. Now, if we've got this fancy, expensive space-based telescope taking these observations of these stars and determining whether there's a dip in light, why do we even need ground-based follow-up? Well, part of it has to do with the fact that in order to do a survey, TESS has to be looking at very large part of the sky at one time. And that means that the camera that it's using has very large pixels. Those of you familiar with doing any kind of imaging, or any of us who have something like a smartphone camera know that every camera has pixels in it. The test pixels are probably, I would say, at least 20 times larger than the pixel on one of the standard CCD cameras that we amateur astronomers have. So because of that, the light from multiple stars could be blended together on a given pixel. And that's one of the reasons we need ground-based observations to split that apart, to see individual stars that are not blended together. And because they're blended together, if TESS sees a dip in light, it might be because that the dip in light is coming about because of a true exoplanet transit, or it might be because of various different false positive conditions. We'll see some of those in a minute. And we therefore need these ground-based follow-up observations to sort out what might be a false positive from a true exoplanet transit. Now, I thought I would show this in sort of a little bit more reality to give you an idea of the difference in resolution between TESS as a space-based telescope versus what we can on Earth. This is a ground-based image that I took from my backyard telescope. And if you look at the two stars in the middle, and if I zoom in on those stars, the little square boxes you see are the pixels of my CCD camera. And you can see that each star covers a good amount of pixels. However, if I superimpose what would be the size of a TESS pixel, that's a ground-based pixel, a TESS pixel would be that. So you can see right away that even though our CCD cameras on Earth can clearly separate these two stars out, a TESS pixel is going to blend them together, and it's just going to be one blob of light. So even though TESS might see some change in light on that pixel, we need ground-based observing to separate out what star it might be coming from. Furthermore, if I kind of now back out and if I zoom out, and that TESS pixel is now covering those two stars, the other complication is that when we do our analysis, we do something called photometry. And in photometry, what we do is we put what's called an aperture around a section of our field of view. From a ground-based aperture is actually pretty small. A TESS aperture, however, is very large. And so not only is the pixel very large with TESS, but also the aperture is very large. So it even complicates further. The bottom line here is that we need ground-based observing to help resolve more than TESS can where that dip in light is coming from. That's sort of the bottom line. Now, what are some of the false positives that we have to worry about? Well, imagine that we have on the left a star, and imagine next to it are two stars that are orbiting each other. These two stars orbiting each other, namely eclipsing binaries, are near the host star. So we call this a nearby eclipsing binary. With TESS, those three stars together might be blended together. So the orbiting two stars that are orbiting each other, that dip in light caused by that, when it's blended together with the star on the left from a TESS point of view, might look like one star with one planet. And so what we do on Earth is we're able to separate out, for example, the star on the left and the two eclipsing stars on the right to be able to better determine where that dip in light is coming from. This is a very common example of one of the things that we amateur astronomers help with the professionals to be able to discern whether, in fact, the dip in light is caused by a nearby eclipsing binary, or whether it's caused truly by an exoplanet across the star itself. Now, if that nearby eclipsing binary is so close to the host star that even on Earth, we can't resolve where it's coming from, that's why in that pipeline I showed earlier, we need to do a higher resolution from a professional observatory. So there are some cases where we still have to go to a professional observatory to see if there's this case of a nearby eclipsing binary happening. We could have the case where a star is orbiting a eclipsing binary, in which case we've got multiple transits happening and we have to sort out if there's a planet in the mix, or if it's, again, just two stars eclipsing each other. We have a case where two stars are eclipsing each other and they're blended with a nearby star, is kind of the opposite from the first case. And we have the same problem of trying to distinguish what's happening. We have the case of just an eclipsing binary where the secondary star is fairly small, and so it could mimic perhaps a transit of a planet. And again, we have to sort out whether it's a star that's transiting or whether it's a planet. And we have a case where a star is grazing another star, and again, it could mimic a planet that is orbiting the host star. So these are all different kinds of false positive cases where we need ground-based observing, in particular amateur astronomers, to help with the professional astronomers to be able to sort out what's happening. We do that by looking at the shape of the curve. If it's a bucket-shaped curve, more likely it's an exoplanet transiting. If it's a very sharp V-shaped curve, then it's a star eclipsing another star. We look at odd even characteristics of the depth. A planet transiting a star should have uniformly the same depth. However, if two stars are eclipsing each other because one is larger than the other, we're going to see different odd even changes in depth. If we look at the observations with different filters, and we see a distinct difference between, let's say, a blue filter and a red filter, then more likely that's two stars orbiting each other as opposed to a planet orbiting the star. And finally, the depth of the star, if it's too large, then more likely it's a star orbiting as opposed to a planet orbiting the star. So these are different ways in which we can help detect whether what we're observing is a false positive or not. To give you an actual example, this is a plot of a light curve of a transit that was done by a amateur astronomer, a colleague of mine, with his observatory telescope. And this was done with a red filter. An odd number of observations later, I did an observation of the same star with a blue filter. And when we transpose each of those on top of each other, we see that there's a distinct difference in depth. So because of the difference in depth of the color and because of the very sharp V shape, this was clear confirmation that these were two stars orbiting each other and not an exoplanet. So this is the kind of observations that we do, the kinds of light curves that we create that indicate whether or not what we're seeing is a transit or not. Now, one of the problems is that I mentioned that TESS has a very large pixel and a very large aperture. So when TESS thinks it found a dip in light, we have to look at stars within a large field around the target star. Here you see, for example, over 100 stars that have to be checked to see whether or not they're the culprit, whether they're in fact the false positive. It was originally the case that the professionals were doing this by hand. And we amateurs, in fact, we on the AAVSO came up with an automated approach where this could now be done on the order of minutes. So what we contributed to the field of exoplanet discovery, in fact, was in this case, not only the observations we were doing, but also software to help the professional astronomers more quickly determine whether what they were seeing were false positives or not. So the contributions that we made so far is that we have been very much involved in the test program. In fact, I did an analysis recently of a month's worth of observations, and it turned out the majority of the follow-up observations were done by amateur astronomers. We helped with develop the guidelines for how members of the test team would submit their observations. Thirdly, as I mentioned, we helped develop an automated process for clearing the field around a target star, whether or not they're false positives. And we're also now helping with observations from some of the large observatories. I myself, for example, on a team with other amateur astronomers where daily we get images downloaded from very large professional observatories in South America, Hawaii, and various other observatories around the world. Very, very large telescopes, very high precision, where we are now entrusted with being able to analyze those precious observations being made by those professional observatories. So these are just some ways in which we amateur astronomers have contributed to exoplanet discovery and science. So where do we go from here? Where does NASA go from here? Well, if you look at the different generations of space telescopes with Hubble and then Spitzer, Kepler, TESS, we're now with Webb, where, as I said earlier, Webb is observing exoplanets in the near infrared and the infrared, and is helping to characterize their atmospheres. Future missions would be, for example, the Roman Space Telescope, expected later in this decade, where we'll be able to start directly imaging exoplanet atmospheres. Now, we're not able to, except in some cases, actually separate out and view a exoplanet from its host star because of the contrast difference. But we are with Roman Space Telescope, hopefully going to be able to take a more closer look at the atmosphere of exoplanets. So to summarize, hopefully I've let you see how we have contributed as amateurs to exoplanet discovery. I want to make the point that those of you who have astroimaging experience already have most of the equipment and techniques for getting into exoplanet observing. So with, in fact, the large telescope that you have at your observatory there, if you are moving it to an imaging-based telescope, that would be an ideal candidate for doing exoplanet observing and analysis. We have the opportunity with TESS to participate in, as I said, real exoplanet discovery. And in fact, those of us who have contributed our observations are named as co-authors on discovery papers. So I'm, for example, already on about 24 discovery papers of TESS observations that have been made. And finally, for those of you who are interested in getting involved in doing exoplanet observing, we at the AAVSO offer training courses, software, forums for mentoring and helping folks who are interested in getting into exoplanet observing. We've already run through a exoplanet course that we've had now for probably about 5 or 6 years. We've already run through about 125, 130 members through that exoplanet course. So a few words about the AAVSO. It stands for American Association of Variable Star Observers, one of the oldest astronomy organizations in the world. Back in the early 1900s is where it started. Its legacy has been observing variable stars and initially visually observing those stars. More recently, of course, doing imaging of variable stars. Data is stored on an archive database. In 2016, we started the Exoplanet database, and that now is one of also a very popular item for our members to get involved with doing science. The organization is involved with professionals, with pro-am collaborations. We are, archiving our observations, as I said, on long-term databases. We have a publication called the Journal of the AAVSO, where we publish papers. We have, as I said, tools and training to help our members do science-grade observations, where we help mentors our observers to be research-grade, kind of observers. And I think it helps with the quality of what then is in our database. We have biannual meetings where we provide a way for folks to interact with each other, and also our meetings now also, just like everybody else, are hybrid meetings, so we have virtual components to it. And we have different sections where we provide courses, guides, alerts, and so on. Our sections cover the range of many different categories of variable stars, different types of variable stars. Some of the sections focus on, such as cataclysmic variables and so on. Of course, my interest is in the Exoplanet section, which, as I said, we started about 6 years ago. And there's a number of courses we've provided. If you go to my website, astrodennis.com, you'll find, in fact, a free guide you could download on exoplanet observing. This is geared for those of you who are doing imaging, deep sky imaging, planetary imaging, for how to get into exoplanet observing. Talks about the best practices for exoplanet observing, and talks about a particular software program that's for free to do those analyses. We have a qualification program for qualifying members of the AAVSO to be full-fledged members of the TESS science team. And I want to mention that we have our, in fact, our upcoming annual meeting is in about a month in Tucson. And if you're out that way, we welcome you to attend. And finally, I just want to mention that we're offering, as we do presentations such as this to local clubs, we're offering a reduced membership rate, more than half of our normal rate. So for $40 for the first year to be an AAVSO member, which gives you the rights to all kinds of different tools and forums and mentoring and so on. If you are interested, just shoot an email to AAVSO@avso.org and just put in club membership in the subject line and your name and the name of the astronomy club. And if any of you do want to get in touch with me, feel free to email me or go to my website where I have all different kinds of resources available. So with that, Frank, I'll be happy to take any questions. Let me unshare my screen. And Frank, if you want to open it up for any questions there, or I guess anybody online, or if there's anything in the chat.
Thank you, Dennis. That was great. That was great. Anybody?
Thank you.
Does anybody have any questions?
Yeah,
Okay.
of the 200, was it 35 or some odd confirmed exoplanets? Was that as many stars, or was that like multiple planets for one star? Do they know that?
That's a very good question. That includes, there are some multiple stars. I think with tests, we probably have discovered at most 2 stars, excuse me, because of the resolution. But yeah, it does cover the number of unique exoplanets, which means the number of stars is somewhat less than that.
Okay, yeah, go ahead.
Yeah, along the same lines, how many, there was what, 5,000 and some odd candidates and 200 and some confirmed. Those are confirmed exoplanets. So how many of those were looked at that were rejected because they were binaries or something?
Good question. I'm gonna say this off the top of my head. I would say about, last thing I think I saw was about 15% maybe get rejected for various reasons. So it's a lot lower than you would think, but
Yeah.
yeah.
And those 231 or whatever the number was, that's strictly from tests. Because I understand.
Yes, that's strictly from tests. Yeah, and that is those have gone through that rigorous process. I suspect that many of those 5,000 we're still working on them, even from the first 2 years. Many of those are ultimately going to get confirmed as well. But NASA, as you saw, has a very rigorous confirmation process.
Dennis, I have a question about, you mentioned the aperture of tests.
Right.
Is that the same thing as when we think of a telescope aperture?
No, what that is if you imagine you've got a star, what you do is you plop on it a circle, and we call that an aperture, and you collect the photons in that circle. And so when I talk about an aperture in this respect, it's not the aperture of the telescope. It's a term, unfortunately, it's the same term used in differential photometry, which has to do with the size of the circle you put around a star to count how many photons are in it. So with tests, its aperture is larger, so it's going to collect photons from many stars versus here on Earth, when we do observations, our apertures are smaller, so we're able to get finer resolution with counting of photons.
Okay. Any other questions? One back here, Cal.
Yeah, when you were talking about microlensing, I'm just curious if you could say a little bit more about that and how it's different from gravitational lensing.
I'm sorry, you kind of broke up. Maybe Frank, you can repeat the question.
Her question has to do with the difference between microlensing and gravitational lensing.
Okay. Actually, the same concept. When we think of microlensing is a form of gravitational lensing. Gravitational lensing, in fact, as you probably saw in one of those James Webb images where you saw that Einstein ring around a foreground galaxy that was lensing a background galaxy. Microlensing is on a smaller scale. It'd be a star system that is causing light to be bent around a distant star. So microlensing is a, if you will, a example of gravitational lensing. It's just of a star in its system versus a galaxy.
A mini version.
A micro version.
Yeah.
Yeah, micro version. Right.
Micro version. Yeah. Any other questions? Has anybody on Zoom got a question? Let's see. Is there anything in the chat? Let's see. That's from earlier. I don't see anything in the chat. Well, Dennis, I think that does it for us. Thank you.
All right.
Very much for joining us. I know it's late where you are. And so we appreciate you staying up late to talk with us.
Okay,
And,
my pleasure.
we'll be in touch because I know we want to take our Ritchie telescope and do some of this work. So
Right.
Yeah, we'll be talking.
All right. Okay.
Great.
Nice
so
to meet
much.
y'all. Okay.
Thank you. Bye-bye.
Bye-bye.
Okay.
Well, that'd actually be kind of fun to do real time.
Yeah, that's what we want to do. Yeah. Yeah, thanks everybody on Zoom who joined us.
So we are gonna be participating in this project.
Yeah. I'm gonna end the meeting. Good night, everybody.